In this lecture, we're going to talk about a problem-solving strategy called dimensional analysis. This is a tool we'll use throughout the chemistry series and can be applied in a number of other fields. And it's really just a way of tackling problems and making them smaller and more manageable to solve, especially conversions and calculations that involve conversions. So let's take a look at this. So it's called dimensional analysis. You might also have seen it referred to as factor label method. And the idea behind it is that units are treated as variables and included in calculations. They can be multiplied and divided and canceled, just like any other quantity. And that allows us to set up problems so that way we end up with the units we need our answer to be. And so it can kind of be a way of creating a strategy for solving a problem when you know one quantity, you need to know another one, and you're not 100% sure how to get in between the two. So this relies on conversion factors, which can be written as equalities. So I can write the conversion between pounds and kilograms as 2.21 pounds equals 1 kilogram. And that would be it written as an equality. I can also write that conversion factor as a fraction, either 2.21 pounds per kilogram or 1 kilogram per 2.21 pounds. Um, and so I could flip it and use it in either fraction form that I need to within my conversion problem. And then when I'm outlining these, I'm always going to follow the general form of information that's given multiplied by a conversion factor to get me what I'm looking for. And so when we're using units to set this up as a determining how to set that conversion up, do I multiply it? Do I divide it? What do I do with it? I'm always going to start with a given unit. I'm going to set up my conversion factor as a fraction. And so I'll make sure that my unit that I want to end my calculation with is on top and the given unit is on the bottom, because then I'll end up, when I do this calculation, I'll end up with let's say my given unit is grams and I'm converting into milliliters. I'll end up with something that's grams times milliliters divided by grams in my conversion factor. And if I'm treating my units as variables, if I have the same variable on the top and the bottom of a fraction, I can cancel them out, leaving me with just the variable or the unit milliliters. And that's how I end up with just the desired unit that I want to have at the end of my calculation. So let's just show a really simple example of this so we know what we're talking about. This is a one-step single conversion. I'll expect everyone to be able to handle three-step conversions easily in this class, or larger ones less easily. So we're starting out with 3 quarts and we want to convert it into liters and then milliliters. So I always start by taking that given piece of information and writing it out. And now I know I need to multiply this by some conversion factor and end up with a value that is in units of liters first. So the way to set up my conversion so I know that I'm performing it correctly and not flipping it and getting the right number is to use my units to make sure I end up at the right spot. So if I don't want quarts to be in my final answer as units, I need to make sure that it cancels out. If I have quarts on the top and the bottom of something I'm multiplying, then I'll be able to cancel them and they won't be units that are in my final answer. And then I'll want to have liters as in my answer. So I'll put it on top so it doesn't cancel out with anything. So this unit that is what I want to end up with is on the top, and the unit I want to get rid of is on the bottom. Now I'm going to use this conversion factor right here. And to make sure I don't flip these, I'm going to make sure that this 1 liter ends up with my liter unit on the top. So we've got one. I'm going to want to make sure my 1.06 quarts is with my units of quarts in my conversion factor. So if I multiply this all out in my calculator, what I'm really doing if I include my variables is multiplying 3.00 quarts times 1 liter and dividing that by 1.06 quarts. So this equals 3.00 divided by 1.06. That's what I'm plugging into my calculator. And the units for that value are going to be quarts times liters divided by quarts. And those quarts are the same on the top and the bottom if they're like variables, so they cancel. And that gives me a value that's just liters. So plugging this into the calculator, I end up with 2.83 liters. Note that I have 3 significant figures in my initial value if it's a measured value, and I have 3 significant figures in my final answer. So they match. I did a multiplication and division step, so I would make sure that my significant figures matched the least number of sig figs in an inexact number from the information I was given. And remember, this conversion factor right here, this is an exact number. Okay, so that's a single step version. So what we're doing when we're solving problems using dimensional analysis is we have to go through these kind of 4 steps along the way. First, we need to sort our information into what is given, what is desired, and what tools do we have to convert between the two. And those are going to be our conversion factors. So sometimes half the battle in a question is determining what is the question asking. And if you don't know that piece of information, you can't actually solve the problem. So once you decide what do I know and what do I need to know, then you can develop a strategy. And this is when we use units to develop a plan for how we're going to use our conversion factors to get to the units that we want. And what do I need to plug into my calculator? Now, the plugging into the calculator part ends up being easy then when we solve it. Once we have a strategy, we know where we're going in the end of our problem, and we line it out with our units, we can input our conversion factors and just plug it into our calculator. But still, we should always double check ourselves, and that's the 4th step. Double checking your answer can sometimes be difficult because you don't know what the answer is. And so it's important to ask the question, is this reasonable? And sometimes that's a hard question to answer because if you're an introductory chemistry student, you don't have a strong intuition yet about what's reasonable and what's not. And we'll work with really tiny numbers and really big numbers too. So I'll try to give you some tips and tricks on how to do that. And just asking yourself simple questions like, do I expect my answer to be a larger number or a smaller number than the number I started with? And if it fits that expectation, then you can have a little bit of a double check there within your strategy to problem solve. So we're going to do this with a practice problem. That's a big multi-step problem. We'll go through all points of our dimensional analysis problem solving strategy. So here is the actual problem. A doctor recommends to a family that they give their 22-pound child 75 milligrams of ibuprofen every 6 hours to help reduce the fever. The family has a bottle of infant drops with a dosage of 50 milligrams per 1.25 milliliters. Now, so to measure the medicine, they can only find teaspoons. It's the middle of the night. It's a terrible time. And these are like baking teaspoons. So how many teaspoons of ibuprofen infant drops should the child get every 6 hours? If you'd like to pause the video and try to map out a strategy yourself first for this problem, I strongly recommend it. And I'll go through and walk through the problem now. All right, so the first step is sorting information and pulling out what do we know, what is given, what are useful tools, what's extra information, what do we need to know. So our given information is that we know that 75 milligrams of ibuprofen needs to be given to the child. We also know a conversion factor that's been given to us. This 50 milligrams is contained in each 1.25 milliliters of the infant drops. So this is what the conversion factor that we have. We know that we have 75 milligrams that we need to give to the child. And we want to know the number of teaspoons, right? So that's following this statement of how many infant drops or how many teaspoons of infant drops should the child get. So that's what we want our answer to be in. So at the most fundamental, we're going to start with milligrams. We're going to multiply it by some conversion factors, and we're going to end up in units of teaspoons. So we're trying to convert milligrams into teaspoons at the end of the day. Now, most word problems actually have extra information in them. In this case, the 22 pounds, the weight of the child, we probably actually won't need to use it because nothing is telling us that we need to calculate the amount of medicine to give the child from a per pound dosage. And we're told every 6 hours it needs to be given, but we're asked how much should be given every 6 hours. So we don't need to use the 6 hour piece of information either. Now, we might not have all of the information in the problem. We might find that there's actually some conversion factors we need to then go look up. We'll find in this one that we're missing a conversion factor that we really need. We're going to need milliliters and teaspoons. We don't have that. So let's set this up. So I always start with what I know and what I want on different sides. So I always start with first, this 75 milligrams of ibuprofen, pile of conversion factors that I don't know what they're going to be or how many they're going to be, and I want to end in teaspoons. So I always like to work forwards and backwards at the same time. So the second I see that teaspoons, I'm going to make sure that my last conversion factor on the top of the fraction has teaspoons as a unit. That means I know it won't be canceled out anywhere else in the problem, and I'll have that unit that I really need. I also know that I do not want the unit milligrams at all. So I'll immediately put that at the bottom of my first conversion factor because I need it to cancel out. So at that point, I could hope that there's a conversion factor from milligrams to teaspoons that I could use. And I don't have that information in my problem. And if I go and look it up, it's not going to be something that I can find. It's a density essentially, or concentration. So I need to find something that goes in between the two. Now, I've been given one conversion that I know will be useful, this 50 milligrams per 1.25 milliliter. So if I am trying to cancel out my milligrams, I know I can put in milliliters from the conversion given to me in the problem. So then I can ask the question, well, if I'm introducing this unit of a milliliter and I do not want milliliter to be in my answer, I know I have to have it on the bottom of a conversion factor. So then I can ask myself the question, do I have a way of converting teaspoons to milliliters? And these are both volume. And so I should be able to look that up easily in an English to metric conversion table. And sure enough, 1 teaspoon equals 4.93 milliliters. So now I have a chain of conversion factors based just on the units that I have to work with that will allow me to craft a problem or a solution to my problem that'll get me from milligrams into teaspoons. And at this point, then I just have to add in the numbers. So let's look at that. So now that I have my strategy, I come in and I add my conversion factors right here, my 50 milligrams per 1.25 milliliters. And I should know where to put each of those values in our conversion factor because they are, I already have the units outlined in the fraction. And then my 1 teaspoon 0.4 per 4.93 milliliters. So then I plug it into my calculator, and I'm plugging in 75 times 1.25 divided by 50 divided by 4.95. And I get this number 0.3803245. It's a long number. There's probably some more digits I cut off. So now I need to decide how to report this number with the correct sig figs. If we assume that this 75 milligrams is an inexact number, then that means it has an important number of significant figures. And looking at it, it has 2. It also has 0 decimal places. Now, both of my conversion factors are definitions, so they're exact numbers. They don't have significant figures attached to them. And I'm noticing that I'm only doing multiplication and division, so whatever my least number of significant figures are, I will report that in my final answer. So even if I have only one value that's inexact, then I'll report the significant figures in my answer that are the same as that one inexact number. So I need 2. So I'm going to round. So the 3 is the first non-zero number. and it's followed by an 8. So that's 2 sig figs right there. The number after that is 0, so it doesn't round up the 8. It keeps it at 8. And so I would report 0.38 teaspoons of ibuprofen. Now, the act of measuring out 0.38 teaspoons of ibuprofen seems completely impossible to me. So there is that. Um, Maybe you just go shy of half of a teaspoon. I don't know. But that's how you can tackle this problem. And then when you want to double check yourself, the question becomes how? So I guess the best way to start, especially in intro chemistry, is just asking yourself, is the magnitude of this number at all reasonable? Um, if I'm starting with 75 milligrams and ending in teaspoons, I know that 1 teaspoon is greater than 1 milliliter because I know 1 teaspoon's 4 milliliters. So, okay. Um, I know that I need more than 50 milligrams of my medicine, and that would be 1.25 milliliters. And so my teaspoons are definitely going to be less than that that like 1 or 2 milliliters. And so that can kind of help me determine that, yeah, it's reasonable to have a number that's less than 1 or 1.25 or 2. And so I can feel a little bit more confident with my 0.38 teaspoon answer. Also, making sure that my units canceled appropriately and double checking that. Writing out my units every time will allow me to be confident that my answer is correct.